I'm Chiu and I'll be presenting to you on chapter 7, yeah? The title for this chapter is Gravitation. Here we will learn about gravity on objects in the universe. Let us look at the course framework. As you can see in this table, there are 3 subtopics in chapter 7. They are 7.1, 7.2 and 7.3. For this lecture, we will only focus on 7.1a, 7.1b and 7.2a. In subtopic 7.1, we will learn about gravitational force and gravitational field strength. At the end of the lesson, students should be able to state the Newton's law of gravitation and define gravitational field strength. First, we take a look at gravitational force. What is gravitational force? Gravitational force is a force that attracts any two objects with mass. For example, we have first object with mass m1 and the second object with mass m2. Both objects will be pulled towards each other by gravitational forces F1 and F2 acting on them. Both forces will have the same magnitude, meaning the same value, but act at opposite direction. In fact, every object, including us, is pulling on every other object in the entire universe. Amazing, isn't it? This is called Newton's universal law of gravitation. Now we are at 7.1a. We will try to state Newton's law of gravitation. Are you ready? Newton's law of gravitation states that every object in the universe attracts another object with a force that is directly proportional to the product of masses of both the objects and is inversely proportional to the square of distance between them. We can also conclude like this. Let us illustrate Newton's law of gravitation. Here we have two objects separated at a distance r apart, where capital M is the mass of the first object, small letter m is the mass of the second object. Meanwhile, r is the distance between the two objects from the centers, and lastly, F subscript g is the gravitational force exerted on each object. Now, what is Newton's law of gravitation trying to tell us? It is trying to tell us that any two objects separated at a distance r apart will experience a gravitational force exerted on each of them. Second, the value of gravitational force depends on the masses of both the objects. Third, the separation distance between both objects will also influence the value of gravitational force. From Newton's law of gravitation, we know that the gravitational force between two objects is directly proportional to the product of masses of both objects, and it is inversely proportional to the square of distance between the two objects. This is also known as a relation. But to calculate the value of gravitational force, we need an equation. To obtain an equation of gravitational force, we need to multiply the relation with a constant value g, where g is the gravitational constant and the value is 6.67 times 10 to the power of negative 11 Newton meter square per kilogram square. How about the distance between two objects? Let's consider a satellite above the surface of Earth or a planet in general. From the diagram, we can see that r is the radius of the planet or massive object. H is the altitude or height of the satellite from the surface of the planet. And r is the distance between two objects from their centers or orbital radius. Note that the radius of the satellite is negligible compared to the radius of Earth. Hence, we find that the distance between satellite and the center of Earth will be the addition between the radius of Earth and the altitude of the satellite. Any small object orbiting a massive object will be known as a satellite, yeah? Testing time! I have 3 questions for you to think about. First, let's say M1 is very large compared to M2. Which force will be larger? Second, what happens to the value of gravitational force if the distance between the two objects is decreased? Third, what happens to the value of gravitational force if the value of M1 is decreased? Check it out, yeah? You can do it. Next will be 7.1b. Here we need to define gravitational field strength. What is gravitational field strength? Gravitational field strength at any point is the gravitational force exerted per unit mass placed at that point. It can be written as such. Gravitational field strength equals gravitational force divided by mass, where A subscript g is the gravitational field strength, F subscript g is the gravitational force exerted on the object, and m is the mass of the object. Gravitational field strength is a vector quantity, meaning it has magnitude and direction, and its unit is Newton per kilogram. Since the unit of gravitational force is Newton and the unit of mass is kilogram, when we combine, we get Newton per kilogram. I have a question. Are we in the gravitational field? Yes, we are, my dears. We are all in the gravitational field produced by Earth. We are experiencing a gravitational field strength of 9.81 Newton per kilogram near the surface of Earth. What does that mean? Gravitational field strength of 9.81 Newton per kilogram means that a gravitational force of 9.81 Newton will be experienced by an object of 1 kilogram in the gravitational field produced by Earth. By using the equation of gravitational field strength, the value of force should be 9.81 Newton if the value of mass is 1 kilogram in order to obtain the value of 9.81 Newton per kilogram. We can also derive an alternative equation of gravitational field strength. Let's say we have a gravitational field produced by a source object or a massive object. Mass of the massive object will be labeled as capital M. Distance from the center of the massive object to a point P in the gravitational field will be labeled as R. Now, if we want to bring an object of mass m or a test mass to the point in the gravitational field, what is the gravitational field strength of this object? Gravitational field strength is the gravitational force exerted on the object divided by mass of this object. Here, we can substitute the equation for gravitational force using Newton's law of gravitation. We can rearrange the equation and simplify it to obtain a new equation for gravitational field strength. Let us recall, from the definition of gravitational field strength and gravitational force using Newton's law of gravitation, we obtain another equation to calculate gravitational field strength, where A subscript g is the gravitational field strength, m is the mass of the source object or massive object, r is the distance from a point in gravitational field to the source object, and g is the gravitational constant. I was just wondering, how much do you really understand about gravitational field strength? Why don't we test? Must be exciting, right? Relax, Kay. I have 3 questions for you. First question is, what happens to the value of gravitational field strength experienced by a test mass placed at a point further away from the source object? Second, what happens to the value of gravitational field strength if the value of m is decreased? Third, what happens to the value of gravitational field strength experienced by a test mass if its mass m is increased? What do you think? Okay or not? Just try your best, okay? So, what is a gravitational field? Gravitational field is a field produced by a source object where a test particle with mass m will experience a gravitational force. For example, if an object is placed very far away from a source object, we will consider that the distance of this object is at infinity. We write r equals infinity. Using equation of gravitational field strength and substitute the value of r, we find that the object will be out from the gravitational field. And using the equation of gravitational force, we also find that the object will not experience any gravitational force. Gravitational field lines of a planet is radial due to its spherical shape. The arrow shows the inward direction of gravitational field. The strength of gravitational field can be observed from the spacing between the arrows, meaning the field strength is weak if the arrows are far apart. Anywhere near the surface of a planet, the gravitational field is considered uniform. Let us take a look at the gravitational field strength at a point outside Earth. Consider a point P outside Earth at a distance r from the center of Earth, where r is greater than the radius of Earth. How does the gravitational field strength change if the position of point P outside Earth changes? By using the gravitational field strength equation, where A equals gm over r square, we find that the gravitational field strength at point P outside Earth is directly proportional to the square of the distance r. The second case will be the gravitational field strength at a point on the surface of Earth. Here we consider a point P on the surface of Earth where the distance from the center of Earth to point P equals the radius of Earth. Thus, the gravitational field strength on the surface of Earth equals gm over the square of radius of Earth. And the calculated value of G is around 9.81 Newton per kilogram. The following case will be the gravitational field strength at a point inside Earth. Let's consider a point P inside Earth at a distance r, which is less than the radius of Earth. Meanwhile, m' is the mass of the spherical portion of Earth with radius r. The gravitational field strength inside Earth is given by the equation A equals gm' over r squared. By assuming that Earth is a solid sphere with constant density, hence the density of spherical portion equals the small portion of mass m' divided by its volume. Mass of the spherical portion is derived using both the equations of density and volume. From the previous slide, we know that the equation of gravitational field strength inside Earth is gm' divided by r squared. After substituting the equation for m' and rearrange, we find that the gravitational field strength inside Earth is directly proportional to the distance r. Subtopic 7.2 is about gravitational potential energy. First of all, we will define gravitational potential energy. Gravitational potential energy of a test mass at a point in a gravitational field is the work done by the gravitational pull to bring the mass from infinity to that point. Gravitational potential energy of a test mass at point P at a distance r from a planet equals the work done to bring the mass from infinity to point P. What is the gravitational potential energy of a test mass at a distance r from the center of a planet? We have learned that the gravitational potential energy equals the work done to bring a test mass from infinity to a point in gravitational field, and work done is the dot product of gravitational force and displacement. So we can derive an equation for gravitational potential energy using the following steps. First, substitute the gravitational force using Newton's law of gravitation. Rearrange the equation and integrate the equation. Finally, we obtain a simplified equation of gravitational potential energy. Let's take a look at the gravitational potential energy equation. Negative sign here indicates that the gravitational potential energy of an object at a distance r is less than its value at infinity, because at infinity, the gravitational potential energy is zero by convention. Let's take case 1. When the body moves away from the planet, r increases. The gravitational force does negative work, and gravitational potential energy increases or becomes less negative. For case 2, when the body falls towards the planet, r decreases. The gravitational work is positive, and gravitational potential energy decreases or becomes more negative. Now, we will discuss about the change of gravitational potential energy over a small distance near the surface of a planet. Suppose that a mass m is moved away from the planet by a small distance h. So, the change of gravitational potential energy of the mass is the difference between the final gravitational potential energy and the initial gravitational potential energy. Substitute the gravitational potential energy equation, simplify and rearrange the equation. Substitute the initial distance and the final distance into the previous equation and simplify the equation. For a small distance near the surface of the planet, we can assume that height h is much smaller than radius of the planet, which means that the addition between radius of the planet and height of the object almost equals the radius of the planet. Hence, the change of gravitational potential energy equals the product of gravitational constant, mass of massive object, mass of test mass, and height of the object divided by square of radius of the planet. Then, we rearrange the equation and substitute with the equation of gravitational field strength near the surface of the planet. Finally, we obtain the equation for the change of gravitational potential energy near the surface of a planet. Let's consider an object at infinity moving towards a lower point as reference level. By using the change of gravitational potential energy, note that the initial value of gravitational potential energy is 0. Thus, the gravitational potential energy at final position, which is a small distance h from the surface of the planet, equals the product of mass of the object, gravitational field strength near the surface of the planet, and height of the object from the surface of the planet. For that reason, we say that gravitational potential energy is the energy stored in an object as the result of its vertical position or height. The energy is stored as the result of the gravitational attraction of the planet on the object. So, we have come to the end of our lecture for Chapter 7. Thank you very much for your attention. Hope that you have learned something from this lecture. Don't forget to watch our next video, okay? See ya!